when we want to create a confidence interval for proportions, the first thing we always want to do is check our conditions. There have to be certain conditions that are met in order for us to even be able to calculate the confidence interval. If these conditions aren't met, there's no reason to even start because we're not going to get anything useful from our information. So, the three conditions should look very familiar. They're the exact same conditions that we had to create a sampling distribution for proportions. So in order to create a confidence interval based on a sample proportion, we need to have data that was collected from an SRS. We need to have a sample size that's less than 10% of the population. And then for proportions, we need to make sure that NP hat and NQ hat are at least 10. Now, this is a minor difference from when we talked about sampling distributions. With sampling distributions, remember, we knew the true population proportion. So we knew the actual proportion for our entire population in question. Now, we're assuming we don't know what it is. So we can't use NP and NQ because we don't know the population P. So we have to use our sample proportion that we calculate to work with our NP and our NQ. So it's NP hat and NQ hat. So number of successes, number of fails have to be at least 10 in each case. Okay? So with any of these problems, the very first thing you would do is list these three conditions and verify that they're actually met. You need to actually make a comment. So on the test, when you guys were asked to do this, some of you just simply said the conditions are met and moved on. Well, that doesn't tell me, A, that you even know what conditions you're checking, and B, that you know how to check those conditions. You have to actually verify. So when you say random, you need to say it was randomly selected or it was an SRS. You have to write that phrase down. When you say 10%, you actually have to show or explain that the sample size is less than 10% of the entire population. And then for your large counts, you need to actually show that N times P and N times Q are greater than or equal to 10. So when you're asked to verify these conditions, you have to write them out and you have to verify in a statement for each one that they are in fact met. Okay? So these are our conditions. If all three are met, then we will proceed. We'll actually create the interval, interpret it, or do whatever else we need to do with it. If any of these conditions are not met, then we would say we can't continue on with our current calculations. There's nothing we can do for the interval if I don't have these three conditions met. Okay? So, remember from last week, the general form of a confidence interval was the point estimate, the statistic. So this would be our sample proportion, or this would be our sample mean if we were working with means. Okay? So we actually calculate a sample proportion. And then we add and subtract the number of standard deviations that we want to move or reach in each direction. So we're going to have our sample proportion be the center of our interval, and then we're going to reach so far above and so far below. That reach is going to be what we're trying to use to capture the true value. So it was made up of two parts, the critical value and the standard deviation of the statistic. So the critical value, remember, tells us the number of standard deviations we want to go. And then the standard deviation is a value we actually calculate based on our formulas from last week. Okay? So that's our generic form. Now, for our intervals, we're going to get specific with exactly what we need to calculate and what it looks like. So, remember, for sampling distributions, so this was something from Chapter 7. When we had a sampling distribution, the standard deviation for our sample proportion was calculated by taking the population proportion, P, times its complement, Q, and then divided by n, the sample size, all inside the square root. Okay? Now if we look at that formula there, can we use that exact formula to get standard deviation for a confidence interval? Why not? Because we don't know P and we don't know Q. P and Q would be population values, the population proportion and the complement of that. So in our case, we need to change up, and it just changes it a little bit, but it is a big difference when you write it out because the notation is completely different. So, first of all, we no longer call our value standard deviation. So it's not SD, we use the term SE, which we're going to talk about in a second. It's called standard error. So the notation changes. It's not a standard deviation, it's a standard error because it's based on a sample value, an estimate. So when we calculate standard error for a confidence interval, we take the sample proportion times its complement, divided by the sample size, and then take the square root of all that. So it looks very similar, but the differences in notation are extremely important. P and Q are population values. P hat and Q hat are sample values. Okay? And like we said, this calculation that we're creating is not a standard deviation, it's now a standard error. The main difference here, last chapter, when we had a standard deviation, when we had the true population proportion, when you guys would set up your distributions, even if you went out and gathered a different random sample, so your random sample would come back with a different sample proportion. But your distribution would be identical because we had the population proportion that we used to calculate standard deviation. When you do a confidence interval, if Eli went out and grabbed a sample, and he captures a sample proportion, his sample proportion will dictate his standard error. And then if Sam went out and collected his own sample and came back, he would have a different sample proportion, which means he's going to have a different standard error. So they're going to create two completely different intervals, A, because they're starting at different points, and B, because their sampling error, or standard error, is going to be different. It's calculated based off of their specific value. Okay? So we're switching gears from population values to using all sample values, which is why we changed the name. Is everyone okay with that idea? So the center of your interval is still going to be P hat, like it always has been, but our standard error is going to be P hat times Q hat over N, all inside the square root. Okay? Now, the next thing we need to discuss, besides knowing the center and knowing the standard error, is we need to know how far to reach, how many standard errors do we want to reach above and below that center point. Now, last week, we said that for a 95% confidence interval, we would reach 2 standard errors in each direction. And that 2 standard errors came directly from the 68, 95, 99, 7 rule. And that rule again said that 95% of all of our observations should fall within 2 standard deviations of the mean. Okay? So we used that 2 as an estimate, how far we're going to reach above and below. Okay? Now, each confidence level changes the number of standard errors that we're going to reach. So every time we have a different confidence level, we have a different amount of standard errors that we want to reach above and below. So to figure out the number of standard errors that we need, we calculate what's called that critical value. And last week, I don't know if we talked about the notation at all, but when we talk about the critical value, the notation is Z star. Z star is different than just plain Z, so it's important that you have the correct notation here. So Z is just a standardized value. Z star is going to tell you the number of standard errors that you want to reach above and below your sample proportion. Okay? So, when we put everything together, our confidence interval will have the form p hat plus or minus z star, our critical value, times the standard error of p hat. You need to know this formula. Now we're going to talk about how to create confidence intervals using this formula, and we're going to talk about how to do confidence intervals in your calculator. You need to know how to do both, because on the tests, especially like on a multiple choice question, they might say, what's the confidence interval for this range? And they're going to put the confidence interval in this format. So they're not going to give you the parentheses with the minimum and maximum value. They're going to put it into the formula. You need to be able to figure out where all those pieces come from. Okay, so you have to know how to do it using both. So p hat plus or minus z star times standard error of p hat. Okay, now, so far, we know how to calculate p hat. That's just taking our sample and calculating whatever proportion comes from it. We know how to calculate standard error. That's the square root of p hat times q hat over n. So two of the pieces we know how to calculate. Z star is something else that we're going to have to describe how to get. So how do we figure out what critical value we use to determine how far we reach in each direction? Okay, so go ahead and get out your calculators. We're going to use those here in a second, because that's how we're going to calculate our Z stars. Okay. Now we'll discuss how to do critical values using the table, so using table A, and we'll discuss how to do it in the calculator. I think when we talk about the two different methods, the one that you guys will choose to do most often will be the calculator. That's why we're going to spend more time on that. Okay? So, we want to calculate the critical value for a 90% confidence interval. Okay? So we got to think about what we're doing here. If I want a 90% confidence interval, an interval gives me a middle percent of values, right? So what I'm looking at here is, I want to figure out what z-scores associate to the middle 90% of a normal distribution. So I want to figure out what z-scores associate with the middle 90% of our distribution here. Okay? So, if we think about that, what we're going to do here is we're going to determine what the z-score is, that z star. And we're going to do it based off of the area under the curve. So what we have to think about here, if I want the middle 90%, what I need to figure out first is what percentage, what area do I need to put into my calculator so it knows what I'm looking for. So when we look at this, I have middle 90%. What does that mean from the outside in the tails? 10 total, right? So there'd be 5% in each direction, so 5% this way and 5% this way, right? So if I want the middle 90%, that means I have 5% above, or 5% above, 5% below in the tails. So if we're talking about, for instance, this cutoff point, and I'm going to talk about why we talk this cutoff point specifically, you can find either one. Okay? One is just going to be the positive, the other one's going to be the negative of the same value. So like if one is 1.2, the other is negative 1.2, right? In our case, though, positives are usually easier to work with. So you always want to go for the higher one is the way I generally do it. Okay? So this is my cutoff point. Now, my calculator, as well as the table, can only ever work with areas to the left of a specific cutoff point, right? So in this particular case, we can't tell the calculator middle 90%. It doesn't have a way to do that. It can only calculate left of a specific cutoff. So if I'm looking at this, even though I'm looking at a 90% confidence interval, so I have 90% in the middle, my cutoff has how much area below it? 95%. Okay? So my cutoff is going to have 95% below it. So when I want my Z star, if I were to do it using the table, we just said 95% is our key, right? That's the area left of our cutoff point. So I would either go into the table and find the closest value I can to 0.9500, and then follow it out to its Z-score. So whatever Z-score goes to that 0.9500, that's my Z-score or my Z-star. Okay? But again, that can be a complicated process. You have a calculator which will do it much easier. So in your calculators, if you want to calculate Z-star, you're going to go to second vars, so get to those distributions. And you're going to use, I think it's option 3, inverse norm. So INV-NORM. All of you should see that option in your distribution screen. Is everyone there? Okay. So second vars, you're going to do inverse norm. Now, for most of you, by the looks of your calculators, most of you should get a screen with a menu, right? It says area, mean, standard deviation, right? So you guys are just going to type in the area that we just got done calculating, the 95%. So you're going to put in 0.95. And you don't need to do the 0, 0. If it's just 95%, you put 0.95. For those of you that get this on your screen, so some of you won't go to the menu, you'll get this. You're going to type in 0.95. Comma, 0 for mean, 1 for standard deviation. So you're going to have a standard normal distribution there. So when you do the 0.95, 0, 1, what do you get for a Z star? Okay? So you get about 1.645, right? Now in this case, I chose to keep 3 places. If we were to use the table, what we'd actually find is that when I look for 0.95 in the table, I have a value of 0.9505 and a value of 0.9495. So these 2 pieces are exactly the same distance away from the point I'm looking for. So this would be 1.64, this would be 1.65, so I would average them to get the actual Z-score. Okay? And when you use the calculator, since the calculator can be more exact than the table can, you want to try to keep a couple more decimal places in this case. So that's another difference between Z and Z star. Z can only have the 2 decimal places, Z star can have more if we're working it backwards. Okay? So our Z score, or Z star critical value for a 90% confidence interval would be 1.645. Now, we could have calculated that same value using this lower cutoff, but instead of putting 95% in, what would we have put in? 5%. So if you go through the process again, go ahead and hit second vars, choose your inverse norm, and type in 0.05 this time for your area. And it gives you negative 1.645, right?
Does the 90% see how the standard deviation is like 2? Will that have any effect? That doesn't affect it at all?
It will, well, because what will happen is, like, if I go for 95%, my 95% is going to be extremely close to negative 2 and positive 2.
Okay, but like the accuracy of it, like can we draw it or anything?
Oh, just make sure, like, I would just use your inverse norm function, get the z-score, and then just plot those z-scores accordingly. So yeah, you don't have to necessarily do the 90% there. Do the z-score first if you're going to draw it, and then, okay?
I'm just kind of confused. If you're doing like 95%, you're trying to find 90, so you're calculating everything but going.
Because your calculator can't distinguish a middle percentage. We are actually calculating the middle 90%. Our middle 90% happens from negative 1.645 to positive 1.645. Okay? But our calculator can only work left of a certain cutoff. So if this is my cutoff, this is the cutoff I need to find, my calculator doesn't distinguish the middle 90. It can only distinguish area to the left, whether it's part of what I want or not. It's going to tell me what that cutoff is from there. So we have to use that 90% plus whatever's in the tail, because that gets us to reach out as far as we need to. Does that make sense? Okay? So, the critical value for a 90% confidence interval is 1.645. Now here, I also have the option of negative 1.645. Why am I able to use either one?
One bit.
Okay? I can use the positive or negative value because in my formula for confidence interval, what am I doing? Plus or minus, right? So I'm going to add the z star times SE, and I'm going to subtract the z star times SE. So I'm going to have the positive and negative already accounted for in the formula itself. Okay? So when you calculate, you can calculate the negative or the positive z star. It's still going to come out the same in your formula because you're going to add and subtract it anyway. Now, what I would suggest is memorizing this z-score. When you have a 90% confidence interval, anytime you do 90% confidence, it's not going to change what your z-score is going to be, your z-star. So every time you're going to create a 90% confidence interval, that 90% is always going to associate with 1.645 as a critical value. And like we said yesterday, 90%, 95, or not yesterday, but last week, 90, 95, and 99 are the most common types of intervals. So 90% is definitely one you want to memorize. You can always plug in your calculator and get the answer, but if you memorize it, it just saves you that much more time on a quiz or test. Okay? And it eliminates the chance of you messing up in your calculator by typing in the wrong area or something like that. So 90%, 1.645, that will be our Z star. If we use that same process, we can find the actual critical value for a 95% confidence interval. Now last week when we talked 95% confidence intervals, we just used the generic 2. But remember that 2 is an estimate. That 68, 95, 99, 7 rule says 95% should be, or about 95% should be within 2 standard deviations. So if we want exact, we need to actually plug it into our calculator to find the real critical value for 95%. Okay? So on the picture here, if we think 95%, so obviously it's going to be a little wider than what we have here, right? So we're going to have something we know it should be kind of out by the 2 and negative 2 here. So if I have my middle 95%, my calculator can't do middle. It can only do to the left. So if I have 95% inside my interval, how much is on the outside? 2.5% on each side, right? So 2.5% down here and 2.5% up here. So in your calculators, you can choose to find the negative or the positive Z star. So either you're going to type in, so if I have 95 plus 2.5, what's my total area? 97.5. So go to second bars. You're going to type in 97.5% as a decimal, so 0.975. 0 for me and 1 for standard deviation. And what do you get for his critical value?
1.96.
1.96? Okay, so in this case, your Z star for a 95% confidence interval is actually 1.96. If you had found the negative version, so if instead of 97.5, you had just plugged in 2.5%, the only difference is you would have found negative 1.96. So either way, you get the same answer because when we plug in our formula, the plus minus takes care of it. So this is another one I would memorize. Z star 1.96 when you're dealing with a 95% confidence level. Okay? While we're at it, let's go ahead and find the 99%. So if I want to do 99%, that means I'm going to have 99% inside.
This would speak to Blake Hammer.
Sure.
Thank you.
So if I have 99% in the middle, how much is on the outside? Yeah, one total percent, so 0.5% on the bottom, 0.5% on the top, right? So in my formula, my inverse norm, I'm going to put in 99.5%. So for the 99% confidence level, we put in 99.5 for our area. And so if you do that, what do you get for a Z star? Okay, so you get about 2.576. And sometimes, just depending on the book you see, they'll round that to 2.58. So you can use 2.576 or 2.58, doesn't really matter. But this is a third one that I would just go ahead and memorize. 2.576. So 90% was 1.645. 95% is 1.96. 99% is 2.576. Okay? If you want, another fairly common confidence level is 98%. So if you want the 98%, that one is generally 2.33. And that's another one you could plug in to your inverse norm. 98% in the middle means 2% on the out. So you type in 99% for your overall area. And you should get 2.33. Okay? So those are ones, like I said, you can always calculate using the formula, but I would just go ahead and have those memorized. It just makes things a lot easier if you do. Okay? So, let's go with an example now. We talked about how to calculate p hat. We talked about how to calculate standard error. Now we just talked about how to find z star. So now we need to be able to put it all together to create our confidence interval. So your teacher has a very large bowl filled with a mix of red and white beads. Suppose you take an SRS of 251 beads from the bowl and you get 107 red beads. We want to calculate and interpret a 90% confidence interval for the proportion of red beads in the container. So basically what we're saying here is we had a very large bowl of beads. We took 251 of them out at random, and we found a specific proportion of red. What we want to do is take that proportion that we calculated and use it to find the confidence interval, to find out what we believe the true proportion of red beads in the jar should be. Okay? So, if this is our scenario, what would be the very first step we would want to take? Even before that. Make sure our conditions are met. Always, always check your conditions first before you proceed. Because if the conditions aren't met, you're going to be doing a lot of unnecessary work by calculating everything out. Okay? So, step one, check your conditions. So this is where you would actually list out. Random. Do we have a random selection? Yes, so it says we have an SRS, so for random, we'd actually say it's an SRS. For 10%, so we're looking at sample size, we took 251 beads. Do we believe that would be less than 10% of all the beads in a very large bowl? Yes. So if it's a very large bowl, we're probably going to have less than 2,500 or more than 2,500 beads in that bowl. Okay? And then the last one is the large counts condition. So the large counts condition is taking n times p hat. Now, when you guys get the information as it's given in the problem here, the number of successes, if they give that to you, is your NP hat. So since they said out of the 251 beads, 107 of them were red, that is NP hat. We got 107 red beads. And then the number of fails, well, if we had 107 red beads, that means we had to have 144 white beads, because together I had to have 251. Okay? So if they give you the values in the problem, so if they actually say, of the total, this is what we got, use those exact values. Because what will happen otherwise is you'll calculate p hat. So you would actually take 107 divided by 251. More often than not, it's not going to come out to be a nice decimal number. Okay? So then if I take 251 times that p hat that we've rounded now, I'm going to get a value that's not a whole number like it should be. Okay? So use the whole numbers if they give it to you. Now, if the problem simply said you found 48% red beads, then you have to do n times p hat and n times q hat to calculate. Everyone understand that? Okay? So there are conditions. They're all met. 107, 144 are definitely bigger than 10. Okay? Next. We want to calculate all of our pieces. So in order to get our interval, we have to have p hat. So we need to calculate that. We need to have standard error. And we need to have z star. There's three pieces we always need for our confidence intervals. So p hat should be pretty straightforward. How would we calculate that? 107 divided by 251, right? So we can take 107 divided by 251 and we get our p hat. Then for standard error. So we start with p hat. We get a value of, in this case, 0.426 when we divide it out. Now for standard error, we use p hat times its complement divided by the sample size all inside the square root. So we found 0.426 for p hat. Its complement would be 0.574. And then we divide by the sample size, which is 251. So we get a standard error of 0.0312. And then z star, you can either plug into your calculator, do the inverse norm function, or if you've already memorized 90% confidence level, would go with 1.645 for our critical value z star. Okay with that? So once we checked our conditions, the next thing is calculate all three pieces that we need. And then once we know what all three pieces are, we can plug them in and solve. Okay? So the next thing we're going to do is calculate and interpret our interval. So to calculate, we need to plug everything into the correct spots. We need p hat, we need z star, we need standard error. So p hat was 0.426, plus or minus. Z star was 1.645 times standard error, which was 0.0312. So then in your calculator, you would do both the addition and the subtraction. Now, in this case, whenever I'm calculating based on the formula here, I go ahead and do the subtraction first, because as you're listing out your interval, you always put the lower value first anyway. So you want to calculate the lower bound and then the upper bound second. So in your calculators, you would take 0.426 minus 1.645 times 0.0312. And that gives you your lower bound, 0.375. Then you would take 0.426 plus 1.645 times 0.0312. And that'll give you your upper bound, which in this case would be 0.477. Okay. Any questions on the calculation part? Anything there we want to go back over or take a look at?
This is calculating confidence.
This is calculating the confidence interval for the proportion of red beads in the bowl. Okay? So, once we get the calculations done, we have our interval, now we need to interpret. So think back to last week, we talked about how to interpret a confidence interval. Who thinks they can give me an apt description or interpretation? Grace?
90% confident that the mean of red beads fall between 375 and 4.4%.
Very close. Very, very close. So she said we are 90% confident that the mean of red beads, what do we want to change there? Proportion of red beads. Okay, so we're talking about a proportion, which means we want proportion in our context. So we are 90% confident that the proportion of red beads in the bowl is between 0.375 and 0.477. Or in other words, we can say we're 90% confident that there are between 37.5% and 47.7% red beads in the bowl. Okay? The other way, if we use the blanket statement from last week, the same thing can be said in this manner. We're 90% confident that the interval from 0.375 to 0.477 captures the true proportion of red beads in the container. So if you memorize this blanket statement from last week, you can always use that. You just plug in confidence level, plug in lower and upper bounds, and then it's just a matter of context at the end, the proportion of red beads in the container. Okay? But you want to make sure you always report the confidence level, you report the actual interval with context. And in this case, you need to make sure you mention it's a proportion is what we're calculating. So it's very important that you have all that in there. We okay with that? Okay. So, using that interval now, the teacher claims that 50% of the beads in the bowl are red. Use the interval to comment on this claim. So the teacher is saying that 50% of the beads are red. Does our confidence interval support or contradict that claim? It would contradict. Why? Because 50% doesn't show up in our interval, right? Right now, we're saying that the plausible values for the true proportion of red beads, the only ones that should be able to work, are between 37.5% and 47.7%. So 50% isn't a plausible value based on our findings, right? So as far as a comment goes, you just need to say something to that effect. Since 50% isn't in the interval, we would probably doubt the claim that 50% of the beads are red. Our interval contradicts that statement. Everyone okay with that? Now if we made the same comment, but they said the teacher claims 45% of the beads are red, Would our interval support or contradict that claim? That would support, because our interval says plausible values are between 37.5 and 47.7. 45% falls in that interval, which means it could be a possibility. Okay? So when you're looking at those and you're trying to interpret, be aware of whether the value is inside the interval or not. If it is, it's a plausible value. If it's outside the interval, then it's not. Okay? All right. Next thing goes along with your confidence intervals. Now, when you're calculating your confidence intervals, one of the things that's going to be extremely important is you're actually going to be gathering the data. Now, in our scenarios, the data is going to be given to you, so you're just going to be using what they give you to calculate. But if you were doing this in the real world, you would have to physically go out and collect the sample, find the value, and then work it through from there. Now, you can determine how big of a sample size you need based on how confident you want to be in your results and how close you want to be with your results. So before we start trying to collect data, the first thing we have to do is decide what sample size we want so that our results have a certain confidence level and as small a margin of error as we want. Okay? So two things are going to come into play here, margin of error and confidence level. So if we think about margin of error was that entire plus or minus portion of our formula. So it involved the critical value z star and the standard error for p hat. So margin of error is always equal to z star times the square root of p hat times q hat over n. So if we're going to try to choose a specific sample size, we're going to have a margin of error in mind. We have to know how close we want to be. And we're going to have a confidence level in mind. We're going to know how accurate we want to be as far as our confidence level. So these two things are going to take care of themselves right off the bat. Now, if we're trying to decide sample size, will I know p hat or q hat? No, because I haven't collected an actual sample yet, right? So when we use this formula to determine sample size, one of the things you're going to do, ME and Z star are going to come from the problem. They will tell you those values. But what we're going to do is use P hat and Q hat at 50% apiece. So P hat at 50, Q hat at 50. That's going to give us our largest possible product, which means it's also going to give us our largest possible sample size, which is what we want. So when you set this up, one of the things you can do is you don't even have to worry about P hat and Q hat because we're always going to replace those with 50 and 50, unless they specify something different, in which case they'll give you a P hat to work with. Okay? So that's what we're going to be dealing with there. Now, as far as solving, I just want to go through real quick what that's going to look like. So, suppose a candidate planning a poll wants to estimate voter support within 3% and 95% confidence. How large a sample do they need? So we have our formula, okay? In this case, our margin of error is 3%, so 0.03. Z star, since we're working with a 95% confidence level, Z star would be 1.96. And then for P hat and Q hat, we're going to go ahead and plug in 0.5 and 0.5, right? So then from here, we would just use the algebra skills and solve for n. So we'll go more in depth in that a little bit tomorrow during our work day. Also make sure you have your calculators tomorrow because we are going to talk about how to do this from the calculator as well. On your way out, make sure you get the assignment because the blogs are still down. You will not be able to get this from the internet.
And David Collins, please come to the attendance office. Mercy Milliken and David Collins. April Withers, please come to the front office. April Withers, thank you.
Are we gonna be able to look at our test?
Yeah, I still have 2 people that need to take them, so. Yeah, if you wanted to head into, so, I'll head into, that's my. All right. Basically, what I'll look at is, it's like some of the questions on the quiz are going to be either pretty much identical to or pretty close to the same types of questions that you had on the test.